Okay, welcome back to lecture 6 of the Introduction to Quantum Mechanics short course. This lecture is going to focus on solvation effects because everything that we've done so far has been in the gas phase, and solvation effects are quite important since most chemistry is done in solvent. Oh, I skipped a slide last time too, so it's a good thing. All right, so the problem, right? Traditional quantum chemistry is carried out in the gas phase. Most reaction chemistry is done in solvation. So the gas phase calculations will fail to properly describe the energetics, especially of charged and or neutral polar molecules involved in a reaction that occurs in solution. Okay, so even when you're doing polar molecules in a nonpolar solvent, so anytime you have a charged species, okay, or a highly polar molecule and the solvent is not, or a nonpolar molecule and the solvent is, you need to really keep in mind how much of an effect the solvation is going to have and need to incorporate it in some way in your calculation. So our possible solutions to solvation, we can do explicit solvation or we can do something called implicit solvation. With explicit solvation, you include the molecules explicitly. You add them to your calculation. The major drawback of that is that you increase your computational costs substantially. Okay, so it's computationally expensive because you're including more basis functions, so your matrices get bigger and there's more two-electron integrals to calculate. On top of that, you can run into a lot of geometry optimization convergence issues. You have to take a lot more geometry steps because the solvent molecules are generally considered weakly bound to the solid. Even if they have hydrogen bonding, they move around a lot and you can get a lot of rearrangement, okay, which adds another level of complexity because if you're doing reaction chemistry, then if you have a lot of solvent molecules included in your calculation, they can rearrange and that will strongly affect the results of your energetics. And you would have to sample lots of different conformations to get average energetics, okay? So usually it's not feasible to include a lot of explicit solvent molecules. So if you do include them explicitly, usually you're only including a very small number of them, 1, 2, 3, and that results in an overestimation of the solvent-solute interaction because you only have a couple of solvent molecules. Okay, so that's the major drawback of only including 1 or 2 of the explicit solvent molecules. So instead you can do implicit solvation, which is some kind of solvent bath, some kind of dielectric with maybe some higher order terms in there, just to give reasonable results for bulk solvent effects, whether that be polar or nonpolar. Okay. For the implicit solvation, one thing that it definitely does not do a good job of reproducing is hydrogen bonding effects, or if the solvent molecule is directly coordinated to your molecule of interest, which happens a lot with transition metals. Okay, so implicit solvation is not going to handle either one of those. It's not going to give you good results if you have hydrogen bonding between the solvent and the solute, or if you have direct coordination. Okay, so let's look at a couple of the different solvation models that are available in most quantum codes, and there are some other types of solvation models that are available too, but these are the most common. So there's the Onsager model, and this is a very, very simple model which makes your solute in a cavity, okay, with a sphere that's like the gyrus of radiation. Oh my goodness, it's never mind. It's a sphere with a radius that will encompass your solute, okay, and then it has a dipole, and that dipole interacts with the solvent. Radius of gyration was the word that I was trying to say. So it's like the radius of gyration of your molecule. Okay, so it makes it a sphere around your solute, and you have a dipole, and that dipole interacts with the dielectric bath around it. Okay, so it's a very, very simple interaction to first order of just dipole. The PCM model is more advanced. Instead of just having this sphere around your solute, it makes individual spheres around your atoms. okay? And it has an interaction of the surface of those spheres with the dielectric bath. So there's more terms that are involved, and you have a better representation of the surface. There are some higher order PCM models. There's something called the isodensity model, which gives you a better interaction because the surface will interact with, or it will respond to the dielectric bath. So it's not a static surface, it is also optimized. And then there's even one that's higher, which is self-consistent, which goes through an iterative process for the surface to respond to the dielectric bath, okay? Generally, you do not see these models in the literature very much, and the reason for that is they have a really hard time converging for all of the molecules that you're interested in your series. And you don't get a substantial improvement in the results enough to try to get past the issue of the optimization. So normally you see the PCM model being implemented. There's a specialized PCM model called SMD, which tried to optimize some of the parameters for the PCM model to get good delta G of reaction within solvent, okay? So the delta G of solvation. And this was parameterized against smaller molecules. So it does a much better job of getting the delta G of solvation values for smaller systems, okay, with the PCM model. Okay, so let's break down the different terms that are included for these solvation calculations to get the solvation free energy. Okay. All right, so like I said, it makes this surface for it, this solvent accessible surface, which is a bunch of spheres, and it's smoothed, okay? The spheres are smooth, so that's what these look like here. All right, so we have for the overall free energy of solvation, it can be broken down into 4 terms. We have an electrostatic term, we have a dispersion term, repulsion term, and cavitation term. Okay. So the electrostatic term is what you expect it to be. You've got charge on the surface, you have a charged dielectric bath, so it's that interaction. The dispersion and repulsion are more of the quantum effect, where you have the stabilization and repulsion in the van der Waals term. Okay. And then the cavitation is how much energy it takes to rip a hole in your solvent, okay, and put your solute in. That's the cavitation energy term. So by default, in Gaussian 09 and Gaussian 16, the PCM models only include the electrostatic term. They do not include these other terms by default. Okay, if you wanted to add them in, you would have to add a keyword to add them in. SMD includes all of them by default. Okay. The Gaussian manual does suggest using SMD, which I think works very well for small molecules, but there have been some issues with much larger molecules where the cavitation term tends to start dominating in different ways and can cause some anomalies. So if you have a very large molecule with a lot of floppy things on it, and you might have where the 2 ligands come and make a void in the middle, you might see some anomalous results for the very big systems. Okay, and you might want to compare between the SMD and some of the other solvation models like in PCM. Okay, so we're not going to go in this in detail, but I wanted to point out a couple of things here. These are all the terms that go into the electrostatic and the dispersion, the repulsion, and the cavitation term. Okay, and these depend on the surface that is generated, this solvent accessible surface, which I showed here. So the way that it makes this surface, and then the size of the little triangles, the little tessera surface elements, okay, is very important for obtaining good results across reaction chemistry. When you're doing, you know, from reactant to transition state to product, because if your surface is changing substantially, then that can have a strong effect on the results. So understand that these solvation models are dependent on, you know, the quality of the surface, how big the surface is, and how it's interacting. And if you do include the cavitation term, how big the molecule is that's replacing the cavity in the solvent. If the cavitation term is dominating, that may not be a term that you want to include in your calculation. So you should be aware and look at the breakdown of the inclusion of especially the cavitation term if you start getting results that are not what you expect or inconsistent with what you're seeing experimentally. Okay, so the way that it makes the solvent accessible surface is it uses a certain radii for each of the elements. And in Gaussian 9 and Gaussian 16, it uses the all-atom UFF defined radii. Okay, so we talked about UFF yesterday. It's the molecular mechanics force field, and they have specific radii that are set up, and that's how it generates all those spring constants, right? So that's how it utilizes and generates the solvent accessible surface. It uses these UFF radii for each element. Okay, and so with the transition metals in different oxidation states, it's using these, you know, very generic static radii that's developed with UFF. So again, it's just an approximation to get a general surface that can interact with the dielectric bath. So how much of an effect can you have with and without solvation? I always like to use this one. It's a nice dramatic illustration of how strong the solvation effect can be, especially when you have charged species. Okay. So this is an illustration of the free energy as you're going from this reactant to an intermediate to a product. Okay, and if you do this at different temperatures, where we have, you know, high temperature to very low temperature, we either have it it's neutral in its free energy change, or it's endergonic. And this is not consistent with what they have seen experimentally, okay? Because these are gas phase calculations. So cationic species in the gas phase, the energetics are not going to be consistent with what you would find in solution. So you add a solvation model. So using SMD, water is the default. Then you get something that is more consistent with the experimental, where at low temperatures it's endergonic, and at high temperatures it's exergonic, which is what they see experimentally. Okay, so without the solvation model, the energetics are completely wrong. Okay, and that's normally what you would find when you have charged species. So you have to include some level of solvation in your calculation. Oh, one thing I do want to mention is all of these terms that are here have special values and parameters for each solvent. Okay, Gaussian does give you the option to put in your own dielectric. Okay, but if you put in your own dielectric, you're going to be using all of the other parameters as if it was water. Okay, the solvent size, the radii of the solvent, and all of the other parameters will default to water values. And the only thing that you'll be changing is the dielectric value. They have a long list of solvents that they have parameterized for the solvation model. If your solvent of interest is not listed in that list, find the one that's closest to what you used experimentally, okay? Otherwise, you will probably not be getting as good of results as you should. Okay, so if you do a solvation calculation, if you do a geometry optimization and frequency with the solvation involved, it's pretty easy to pull the results out. But more often than not, you're doing a geometry optimization and frequency calculation in the gas phase, and then adding on a correction for the solvation effect. And that's because geometry optimizations in solvation take substantially longer. They tend to wander around and take a long time to reach convergence. Sometimes it's necessary, and if your system behaves well, it's easier if you can optimize to do the frequency and solvation. But if they misbehave, normally you're doing a gas phase optimization, and then you're just correcting the energy with a single point solvation calculation, like a single point PCM calculation. So that means you have to take the results and piecemeal together the energetics. So you need to take the overall energy that you get from the single point solvation and add on the correction to the free energy from the gas phase optimization and frequency. So the energy of the solvation plus the correction will get you the total G of solvation, including all of the vibrational contributions, okay, and the other entropy contributions from the frequency calculation. Okay. So if you're going to include solvation by doing gas phase optimization and then just a single point to correct the energy, then you need to go through a procedure like this and add the values together. Otherwise, you just do an optimization and frequency together and you pull out the free energy just like you normally would for a gas phase calculation. So this is often okay. I'm making the grand assumption that the geometry is not going to change substantially from the gas phase to solution. If you suspect that the geometry is going to change substantially, you definitely want to check. Okay, on a couple of points, data points, then you want to run single point or optimization in gas phase, do a single point solvation, and then optimize in solvation also. Okay, and do another one and compare those energetics and see whether or not you're getting substantially different results. Okay, so earlier today we did excitation calculations on acrolein, and we did them in the gas phase. Often when you're doing time-dependent DFT, you're comparing it with something that's done in solution. So you want to incorporate those solvation effects. So if you just use the solvation model, then it will only get those, you know, the first order in the, it won't handle if you have hydrogen bonding. And this paper illustrates that effect where it's missing the hydrogen bonding. So if you have a protic solvent and you have hydrogen bonding capabilities, your results are not going to be as good as they should be. So here are the experimental values for these 3 compounds in protic solvent. And this is what PCM gets for the excitation. So it's qualitatively correct, but not very quantitative, okay? So they add in some explicit solvent molecules, and the results actually get worse, okay? And this is where you run into problems with where do I put my explicit solvent molecules, okay? You can really mess up your results by only having 1 or 2 and having the overbinding. So this is where you have, I believe, both the solvent and the solvation model on there, and you have more of the solvent molecules, and you're getting much better results compared to the experimental. And then they even went further and they did some molecular dynamics and sampled multiple conformations and found lots of different conformations and calculated those and incorporated that in their results. Okay, but you know, the PCM, it's still getting qualitative results. It's just not getting the quantitative results because it's missing the hydrogen bonding. But if you incorporate explicit solvent and you do it wrong, then you're actually going to make your results worse, okay, in some instances. So you need to be careful about the placement of your explicit solvent molecules. Okay, so we're going to talk about partial charges a little bit because it's like the #1 question that I get when people start doing calculations is they want to calculate the partial charges to explain the results. They want to know where the charge is localized. So I'm just going to talk about a number of the different partial charge schemes and partial charges in general. So there's quite a few schemes that are available. The one that you get out of pretty much every calculation is the Mulliken population analysis. Okay, and this is a very, very simple procedure to get the partial charges. The one that is heavily used for generating partial charges for molecular mechanics calculations is the molecular electrostatic potential algorithms. Okay, normally the Mersing-Coleman or C-help-G. Okay, but we'll talk about each one of these. So partial charges, as I mentioned, I think in the first lecture, the electrons are shared. You know, they don't belong, this electron doesn't belong solely to this atom. This electron doesn't belong solely to that atom, okay? And the ones that are being shared, they're not shared equally. right? So the electrons don't really belong to an atom, but we really like to assign them to atoms. It makes our interpretation a lot easier. So we have these different schemes that will generate, sorry. We have these different schemes that will generate partial charges. Mulliken population analysis, basically all it does is you've got your overall number of electrons, okay? You have all of your, these coefficients. Remember the coefficients of the basis set? That's the coefficients that go in front of the atomic orbitals. You have the diagonal terms for the coefficients, and then you have off-diagonal terms. And then there's the overlap, how much the off-diagonal, so the coefficients that are on different atoms overlap, okay? So that's the overlap term, where you have bonding between the atoms. Okay, so this density can be assigned to a single atom because these are atom-centered functions, right? So we assign this to the individual atom that it's on, and then the off-diagonal terms are basically just split in half. So anything that's off-diagonal, where you have the basis functions on different atoms, it assigns half of it to one and half to the other. Okay. So it's a simple scheme, easy to calculate, very fast. You get it with any quantum calculation that you do that has electrons, okay? And the problem with it is that splitting the atoms, or splitting the electrons equally, the density equally between two atoms is not a really realistic description because these bonds are polar, okay? So while this is a nice simplified scheme and it gives you something to work with, it's not really the best way to think about assigning partial charges, okay? So you don't want to look at absolute values of these partial charges. You want to look at trends for the partial charges, okay? So if you're going to utilize partial charges for anything of analysis like, you know, we've lost electron density on this transition metal as we've added this ligand, you want to look at trends in the partial charges, and you never want to base an analysis solely on partial charges, because partial charges are not a physical quantity, okay? They're something that we utilize to assign density to see where density flow is, okay? So never draw conclusions strictly on partial charges. Okay, so just real quick, there's something called atomic polar tensors. Atomic polar tensors, you only get them with frequency calculations because it requires the second derivatives. I just want to mention really quick that this does not conserve the dipole moment. Sometimes you get really crazy partial charges. On very electronegative atoms, they'll become positive. So it's generally not heavily used in the literature. Okay? And you only get them with frequency calculations. This one is just mathematically rigorous. It has nice mathematical form. The atoms and molecules. It takes the density, it looks for the zero flux surface, and then it assigns the density that's within the zero flux surface to the atom that is contained within the zero flux surface. So it seems like it's a wonderfully mathematically sound way of assigning density to the atoms, but often it comes up with, again, some partial charges that are not really consistent with what we know about the elements in general. Okay, so it's intuitive, but often doesn't give you intuitive results, right? So it tends to overestimate the charges in the polar bonds, and it also does not conserve the dipole moment. I'm sorry, this should be a wave function. So I'm going to fix that right now. Okay, so the molecular electrostatic potential, which we did during our first hands-on session, I showed you how to generate one of those. You just take the density and you map the electrostatic potential on it. Okay, and the electrostatic potential, all it does is it takes a fictitious point charge in space, okay, and it looks at its energetic interaction with the density around it. Okay, so you have a grid of these point charges, Okay, and those point charges, the energetics from its interaction with the density gets mapped to a density surface, which is what is shown here. Okay. You can generate partial charges. There's different schemes to generate partial charges that will reproduce this electrostatic potential, okay, that is rigorously calculated from the density. Okay, so these are the schemes that are most common for doing that. And you can also request that it will conserve the dipole moment. Okay, but you do have to understand that the partial charges that are generated from this calculation are not unique. Okay, you can come up with a whole new set of partial charges that will perfectly reproduce the electrostatic potential. Okay, so the scheme uses restrictions to make sure that it's using reasonable partial charges. Okay, and you can add on that extra restriction so that it will reproduce the dipole moment. Okay, so I do consider it to be one of the better methods to calculate partial charges, and it is the one that is used generally for generating partial charges to use in molecular mechanics calculations. So if you do decide that you want to calculate and assign partial charges for your molecule, I would suggest looking at the MEP method, C-help-G or MK, to generate those partial charges for your interpretation of some of the results. But like I said, don't ever draw conclusions solely on partial charges. Okay, so this is just a table showing changes in partial charges at the different levels. So this is a carbon in methane. If you're looking at Mulliken, this is, very small, single zeta, double zeta, right, triple zeta, but up through the correlation consistent, the Mulliken at one point becomes positive for the carbon, and then the rest are negative. Okay, same thing for some of these other ones, but you'll notice that the ESP fit is pretty consistent. I mean, there's variation, but it's not substantial compared to what happens with the Mulliken. Okay, and then the AIM also has some funny spots depending on the basis set. Okay, but then it all becomes positive, whereas with the ESP, it's negative, which is more of what you would expect. Atomic charges for oxygen in water. Okay, so here we are all negative. It's not too bad, but it is jumping around a bit. Okay, ESP is fairly consistent, especially when you do the larger basis sets, it stops changing substantially. Okay, the AIM is in line, at least it's negative this time, but it is more negative than we'd probably expect it to be. It tends to overestimate. Okay, so, which is why I like the ESP fit. This is just a nice graphical representation of how much spread you can get in the partial charges with the basis set and the level of theory. That's why you want to look at trends and not the absolute values for these partial charges, using the same level of theory and same basis set for whatever you're comparing. You can do some additional analysis if you're interested in looking at properties of bonding. The AIM analysis may not give you very good partial charges, but you can look at the AIM analysis to find what are called bond critical points, ring critical points, or cage critical points. It just tells you where there are certain characteristics in the density. So a bond critical point is a saddle point in the density in between two atoms. Okay, so for instance, with these three molecules, all of these have a bond critical point in between the two transition metals. Okay, that doesn't tell you anything about the strength of that bond. It just tells you that there's a saddle point in the density between those two atoms. So regularly, people will want to know whether or not there's bonding in between two atoms, or if it's just being, forced there, or what kind of interaction you have. So if you want to show that there is a saddle point in the density, you can do an AIM analysis, and it will tell you that there is a bond critical point or not between those two atoms. Okay, so for these, there's not. You can also look at the character of that bonding by looking at the Laplacian. Sometimes that will give you some additional information about whether it's more ionic or covalent in nature. So this is a carbocation. right? It's a fluoride and carbon-fluorine bond. So we have a bond critical point between both of them, but it doesn't tell you what kind of bonding it has. And if you look at the Laplacian, this is indicative of a covalent type interaction, and this is indicative of an ionic interaction, which is consistent with a carbocation interacting with the electronegative fluorine. Okay, so a lot of people like to calibrate against IR spectra. So I'd like to, we've already done frequency calculations and looked at some of the vibrational modes in one of the earlier hands-on sessions, but I want to talk a little bit about IR spectra and remind you that our frequency calculations are to first order. Sorry. We have the harmonic approximation for our frequency calculation. So the higher you go in the vibration, the bigger the error is going to be. Okay, because our vibrational well is more Morse-like, and sometimes it's substantially Morse-like. Okay. So to get the IR spectra, you have the vibrational modes, okay, and then it also calculates the intensity. So you'll get both the intensity and the vibrations, and you can calculate the IR spectra. Now, one thing, since we do make a bigger error as you're going up in frequencies, it's common to scale them, okay, by some scaling factor. There's not a single scaling factor to use. It really depends on your system of interest. You have your experimental spectra, you have your calculated spectra, and you multiply the frequencies by a single scaling factor. DFT is usually somewhere around 0.98. It could be higher than that, it could be 0.99, it could be 0.96. It's usually somewhere in that realm. Okay. And the reason that we use the scaling factor is because our error is higher as you go up in the frequencies instead of a shifting factor. So sometimes actually more often than not, interpreting the IR spectra is more complicated than what occurs with a single system. So you might do a calculation on a single molecule and it doesn't match your experimental, okay? And that could be maybe because you're using a molecule that is not actually what's in your solution. It may have a different form, different conformation. There's a whole host of reasons why your calculated spectra does not align with the experimental spectra. You could also have a combination of compounds in the spectra. Okay, so this is just an illustration that after trying all possible proposed molecules for a spectra that it was obtained, the only way to reproduce it was by having a combination of the species. Okay, 60% of species 1, 40% of species 2. No other species hypothesized would reproduce the experimental spectra. So it was actually a combination of molecules in the experimental spectra. So you can also calculate the Raman spectra. However, for Raman spectra, it requires the third derivative. And DFT calculations have a numerical component. So the third derivative requires a numerical frequency calculation to get the intensities for the Raman spectra. Okay, so that's computationally intensive. The first calculation we did on day 1, if you looked at the results, it was a Hartree-Fock calculation, and you did get the Raman spectra. And that's because it can do the Raman intensities analytically for the Hartree-Fock calculation. So you will get both the IR intensities and the Raman intensities. But for DFT, by default, it only gives you the IR intensities when you do a frequency calculations and not the Raman. And like I said, that's because it has to do it numerically. So there's a substantial increase in computational cost. Okay, so if you're interested in doing Raman spectra, expect that your calculations will take substantially longer. You have all the frequencies, you just won't get the intensities. Quantum calculations are also often used to compare against NMR experimental results. To do NMR calculations, the NMR, gets a splitting of the nuclei. So the NMR calculations are not too terribly intensive. as long as you're not including spin-spin coupling. So if you're just looking at the shift for the NMR calculations, it's not bad. But one of the things that you have to keep in mind if you're going to do an NMR calculation, it gives you the shift for all of the elements, not just carbon or hydrogen. It gives you the chemical shielding and shift for all of the atoms. But the absolute shifts don't really mean anything. It's just like the absolute energies. You need to have the standard. Okay, so when you're doing an NMR experimentally, the machine is set to a standard. Okay, whether that be the TMS or the solvent, there is some type of standard, and everything is relative to that standard. You have to do the same thing computationally. You have to do an NMR calculation not only of your molecule of interest, but also the standard. And then you take the difference between those two, and that's what you compare with your experimental. It can be very useful to determine what kind of molecule you have. We're not going to spend too much time on this slide. If you want to go back and look at it, it's just showing different levels of theory and the quality of the results that you might expect to get for carbon and hydrogen. Okay, the hydrogen shifts are quite small. You can get, if you're comparing two things and the parts per million shift is very small between two different hydrogens, you're probably going to have a hard time resolving that with a calculation. Okay. You get larger errors with carbon-13, and for the heavier elements, the errors get even larger. Okay, so this paper just kind of goes through the different quality of results that you might get for the different levels of theory. NMR calculations can be very useful for determining what molecule you actually have in your system if you don't have a crystal structure and you're unsure of its actual configuration. So if you have some NMR and some other experimental data, you can resolve what you actually have in solution. So this was just an illustration of, this was the proposed structure based on literature, but the NMR of that proposed structure was not consistent with what they had experimentally. This molecule, which was lower in energy, was actually consistent with their NMR spectra. Okay, so between the energy and the consistency with the NMR spectra, you were able to resolve what the configuration of the species actually is. Okay, so we're going to do a grand summary of what we've covered, and then we'll take a small break, and then we'll move on to the last hands-on session, which goes over solvation calculations. Okay. Okay, so what we've covered in these 6 lectures is a basics of quantum mechanics. And like I said on day 1, if you don't have a background in this and you've never done these types of calculations, I really don't expect you to be able to just go do your research all by yourself. Okay, you really need to work with a group and have some people that you can collaborate with, and definitely go to the literature and reproduce some results. Okay. There's a fair learning curve to these quantum mechanic calculations, and there's so many options out there that you really need to have some support when doing them. Okay, so the basis of the quantum mechanics is solving this time-independent Schrodinger equation. You have this Hamiltonian operator, operates on this wave function, right? The eigenfunction gets you the energy of the system. Okay, remember the Hamiltonian is our levels of theory. So the ab initio series, DFT, semi-empirical. Okay, and then this is the wave function. This is that linear combination of atomic orbitals. Our basis set is the thing that we use to describe the mathematical form of the wave function. Okay. So our wave function is represented by that linear combination of atomic orbitals. Okay, so our basis set names have those coefficients and exponents. And the vast majority of quantum codes use Gaussian type orbitals, which is the e to the minus zeta r squared. But there are a few select pieces of software that use the STOs, which is e to the minus r. Okay. Approximations made in the Hamiltonian. In the Hamiltonian, it generally neglects relativistic effects unless you do a specific type of calculation. We include these relativistic effects using an ECP, an effective core potential, instead of explicit electrons for the core electrons of very heavy elements. which was developed with a relativistic Hamiltonian. We neglect coupling of electronic states, okay? And more importantly, we neglect the coupling of the electronic and nuclear motion, the Born-Oppenheimer approximation, which means we optimize the wave function, then we take a geometry step, we optimize the wave function for the new geometry, then take a step. So the motion is decoupled. We assume that the electrons are moving so fast that they see static, unmoving nuclei. The ab initio summary, Hartree-Fock through couple cluster of singles and doubles. Okay, we have an increasing amount of this all-important dynamic electron correlation. That's the correlation of the electrons of opposite spin that try to stay away from each other in the same molecular orbital. Okay, so Hartree-Fock is not included at all. And CCSD in this series includes the most, the CCSD parentheses T. So it's a nice hierarchy, but the cost rises substantially as you move up this hierarchy. The pros for density functional theories, it includes this dynamic electron correlation for about the same cost as Hartree-Fock, which is nice. It's often more robust for systems with multi-reference character, like transition metals, first-order transition metals, and it's not quite as dependent on the quality of the basis set compared to those wave function methods. But the major drawback for DFT is there's no real good hierarchy for DFT, okay? You can't, going from this functional to this functional is not necessarily going to get you more dynamic electron correlation. It's just getting you different dynamic electron correlation, okay? And it's, most of the functionals out there are poor for dispersion, okay? Some of the corrections that have been added to work on that, and some of the newer functionals have tried to incorporate it. But for the vast majority of functionals out there, they're quite poor to get the dispersion energy, which is very important when you have things like phenyl-phenyl interactions, okay, where you have a lot of bulky groups that are tightly packed together. Now remember, for all of your calculations, you need this basic information. You need the molecular coordinates, all of them, including the hydrogens, okay? You should know whether or not your molecule has symmetry, what point group it might be in. You need the overall charge of the system, okay? Not the charge on each atom, but the overall charge of the system. And you should know how many unpaired electrons you have. If you don't know how many unpaired electrons you have, you can calculate with different spin states and compare those energetics. Okay, but you have to make a decision on how many unpaired electrons you have. You need to choose your level of theory to do a calculation. How do you choose? You go to the literature, you ask somebody with experience, but generally go to the literature, right? See if somebody's already calibrated against some system that's similar to yours. Okay. Also have to choose a basis set. Again, you go to the literature, see if somebody's already calibrated, or collaborate with somebody who has a background in that similar system. So most importantly, I have here in bold, calibrate, calibrate, calibrate. Okay, we have a lot of approximations. We have a truncated basis set. We have an incomplete Hamiltonian. Okay, so you need to calibrate against something, against experimental data, against benchmark calculations, something. Okay, so that is the end of lecture 6. Let's go ahead and take about a 9-minute break, and we'll get started with the hands-on session at 3 p.m. Okay, let's go ahead and get started with the last hands-on session. If you haven't done so already, please log into your video portal. Okay, after you get logged in and you open up your desktop, you should see a new file available. If you do not see that new file, go ahead and open this up, go to your desktop, and refresh your desktop, and then it should show up. Okay, so what we're going to do in this hands-on session is we're going to, sorry, give me just 1 second. Okay. So we're going to calculate the vibrational spectra of formaldehyde, and we're going to compare it with the gas phase experimental spectra and the results of the experimental spectra in acetonitrile. Okay, and we're going to look at the CO stretching frequency. So I'm going to have you calculate formaldehyde in the gas phase, and you're going to find a good scaling factor to compare to the experimental gas phase number, or gas phase spectra, that's what I meant to say. So here's the gas phase spectra. You can get it from this webpage if you want to pull it up and actually download the data. It comes from there. And then we're also going to go through and run calculations with just the PCM acetonitrile solvent, so the implicit solvent. Then I'm also going to have you run it with explicit acetonitrile. And that's what this file is here. This file is one that I've already drawn for you to use, okay, where you have both the formaldehyde and the acetonitrile. Okay, so I give you what level of theory and basis set to use for the geometry optimization and frequency calculation. Now remember that you have to do a frequency calculation to get the vibrational modes, okay? And the frequency calculation is also going to calculate the IR intensities. You have to optimize because the frequencies will be horrible if you don't optimize first. And that's because we're using that first order approximation. Right? So the frequencies are only good at the stationary points. Otherwise, you get really poor results because it's very anharmonic on the rest of the potential energy surface. Okay, so I give you instructions on what level of theory and basis set to use, and then I leave it to you to set up your input file. Okay, it's good practice. Right? And while that calculation's running, then I have you set up your PCM calculation. Okay, adding in the PCM solvation. Then while you're waiting for that one, go ahead and set up using the mol2 file that I've given you. And then when you're done running those calculations, you're going to go ahead and open them up and look at the results. And you can pull up the you can pull up the computed gas phase spectra within GaussView. And in there, you can change the broadening and the scaling factor, okay, and try to make it look similar to what is published for the experimental spectra in the gas phase. Okay, and that's how you're going to determine your scaling factor. And then we're going to apply that scaling factor to the results that you get with the PCM and the explicit solvent calculation. Okay, and see how those results come out for the CO stretching frequency. So this one here is the CO stretching frequency, which is at about 1723. Okay, reciprocal centimeters. And then I also give you a few, this is the one in acetonitrile. It's pretty rough. So it's this one here. And this is the CO stretching frequency, which is at about 1709 in the spectra from 1954. So if you find a newer one, please let me know. Okay, and then I also give you some Linuxy command line commands if you want to pull some of those results out. So you might want to give those things a try. Okay. So these calculations are just to give you a feel for the effect that solvation can have on your results. Let me just show you this real quick. So I want you to notice a couple of things. This acetonitrile is strategically placed, right? So I'm looking at the effect of acetonitrile on the CO stretching frequency. So you would think that you would put the acetonitrile where the CO is, but the acetonitrile is not really going to interact that strongly with the oxygen. What the acetonitrile is going to interact with mostly are the hydrogens on the NH2 component of your formaldehyde. I also want you to note that the formaldehyde is planar, right? okay? And that's because we get pi distribution. So the lone pair that's on the nitrogen gets distributed, okay, along with the pi system in the CO. And that's why formamide is planar, okay? It's like a peptide bond. All right, so if you put your acetonitrile somewhere else, it's going to wander around for a long time, and you may not even, you might get a failed geometry optimization due to excessive number of geometry optimization steps. So the location of this acetonitrile in the starting structure is very important. You don't want it too close. Let's see if I can get it to go. No. You don't want it too close. You don't want it too far, okay? You want it at a reasonable distance for hydrogen bonding. Okay, you can definitely have some wiggle room there, but you definitely can't have it too far. Okay, so I've given you a good starting structure, but if you want to tinker around with it to see how much effect the starting structure has on how long your calculation takes, you can try moving it around, okay, and seeing how much longer it takes for your calculation. Like if you take this and bring it over here and have the nitrogen in proximity to the oxygen, it's going to be unhappy. It's going to push it off. It's going to do all sorts of interesting things. So your starting structure is very, very important. Okay, so that's all I really have to say to get started with this. So I will go ahead and stop recording at this point and let you get to work. And if you run into any problems, let me know. And at about 3:50, I will come back and go over the results with everybody. Okay, let's go over some of these results. So I don't know if anybody was looking at my screen, but if you were, you would notice that there was a sudden change in the spectra. Okay, so if you have your PDF document open, go ahead and move it to where it says infrared spectra, and then look at the title and tell me if you see anything wrong. Did anybody happen to notice that the results for the gas phase weren't lining up very well? With the values that were listed in the PDF? So by a show of hands, who got their spectra up from the formamide gas phase optimization and frequency calculation? Okay, excellent. So go ahead and go into your PDF and refresh it, because that was dimethyl formamide. That was the spectra, okay? So this is the formamide spectra, and there's a substantial shift in the CO stretching frequency when you put two methyls on it. Okay, so here we have our gas phase formamide. I'm going to go to results and vibration. Okay, and here's where you can say whether or not you want to scale the frequencies. Okay, so if we want to just go straight to where the CO stretching frequency is, it's going to be this one right here around 1700. Okay, but if you're not sure, you can turn on those displacement vectors, right? Try to click on the right one. Increase the scale. Now, for the vast majority of the time with the stretching frequencies, it's not going to be a single mode. There's going to be coupled modes. Okay, so you can roll through the frequencies that you have until you find the one that is most consistent with the stretching frequency of interest. Okay, so it's not just the CO stretching, there's also, you know, some bending and a couple of other things going on, but the vast majority of the motion is the CO stretching. Okay, so this is the correct one that we are interested in with the CO stretching frequency. And what we've calculated for the gas phase is 1790, and what they have experimentally is 1770. So if you'd like to find a scaling factor, you can put it in here. Okay, 0.98 is a little bit too much for that. You can also look at some of the other ones and try to fit with the other excitation. Now you also notice that there are more peaks in the experimental than what we have in our calculated. So if you want this to compare, you can go into the properties, okay, and you can change invert and the scaling or the broadening, okay, so that it looks more like the experimental. Okay. One of the things that we're missing in ours is vibronic coupling. Okay, so sometimes those peaks will split a little bit with vibronic coupling, and we don't have that in our calculation. It's all to first order. And you can also change it if you wanted to change the range, so it's just the same range. You can do a fixed range to compare with the spectra. Okay, so right now I have a scaling factor of 0.98, which seems like it may be a little bit too much. Okay, so I can change it to 0.99. Okay, I'm not sure if I have exactly the right overlay for the, I think it's pretty close. Let's see, where's the 3500? Yeah. Okay, so that's looking pretty good. Okay, if you wanted to do this a little better, you would definitely want to overlay them in reality, but 0.99 looks pretty good here. Let's see what value we have. Okay, so what you want to do is split the difference with all of them. So we have 1770, and here we have 1772. Okay. So 0.99 seems quite reasonable for this gas phase compared to the experimental. So we don't have a lot of anharmonic contribution here, and our level of theory has done a reasonably good job of reproducing the gas phase number. Okay. So the next thing that you would want to do is take a look at the other results. So here we have with the solvation model, if we wanted to put in our scaling factor of 0.99, experimentally there was a shift . What was the experimental for the acetonitrile, or formamide in acetonitrile? It's right down here to 1709. Okay, so here we have gone just a little bit below that with the scaling factor to 1698 with the PCM model. Okay, so let's try looking at it with the explicit acetonitrile. Now, I want you to see that the geometry changed substantially. Right? Remember, I had it sticking out, and then it flipped around in the gas phase optimization. Let's go ahead and look at, oh, and I think it failed. Okay, so why do I think it failed? I think it failed because I don't have vibrations. So it might still be running. I have to go look at that. Let's go to, I should have one more. Yes, this one. So let's see if this one finished. Okay, you'll notice with the solvation model, it stayed in that same orientation as the starting geometry. It didn't flip around like that. And that's because now the acetonitrile is happier with the dielectric bath around it. Okay, so let's go ahead and look at what we got for our frequency there. Okay, so we're still at about 1693 for the CO stretching frequency. Okay, but the geometry is more of what we'd expect it to be. Right, so getting the solvation effects, yeah. So somebody else said mine failed too. So let's take a look at why it failed. Maybe it ran out of geometry steps, which is probably what it did, but let's see why. I'm gonna go ahead and close this. So this is very common when you have multiple molecules in your calculation. Did it fail or is it still just running? So I don't see an error termination. Yeah, no, mine's still just running. You want to check to see if yours is still running or do you have an error termination? So when you have two molecules that you're trying to optimize and you are far from, yeah, it's still running, right? So you'll notice how much longer this geometry optimization is taking. And that's because it's having to take a lot of steps, okay? And it has weak interactions. And the reason it's having to take all those steps is because it was far from the optimized geometry. Okay, so that'll probably keep running for a little while. Right, so this is just an illustration of the complexity that you have to deal with when you need to incorporate solvation effects, especially when you have some kind of strong interaction like hydrogen bonding with the solvent. Okay, and you usually have to run multiple calculations until you get a good balance between computational cost and accuracy of the results. Okay, but for any calculation where you have a charged species, okay, you definitely need to include solvation. And anytime you have where the solvent molecule is coordinated to the molecule or intimately involved in the reaction chemistry. Okay, so that ends this introduction to quantum mechanics short course. You will still have access to these accounts until tomorrow morning. So if you want to continue to play around with some of the hands-on exercises, feel free to, but you will be locked out of the accounts early tomorrow morning, somewhere between like 8 and 9 a.m. So if you want your files, don't forget that you can download them. If you go back to your interactive session, you can go to Files. Okay, and you can select, if you go to your desktop, you can select this and just drag it. Or sorry, if you're on a Mac, don't drag it. It makes links. So if you're on Windows, it actually downloads them. So my suggestion is that you highlight them and then you just click download. Okay, and it will download the files for you and it zips them up. Okay, so if you select all of it, then it will try to zip it up and download the whole thing. Okay. Okay, so if you could please, for those that are still on the session, we have a survey that helps us tune our future short courses, if you would be so kind as to fill it out before you log off. And I will stay on the line for another probably about 6 minutes if you have additional questions or you want me to look at something. Okay.